Our first plenary talk this morning is from Dr. Elizabeth Slate, who is the Doug McLean and Pearl Levine Fairweather Professor of Statistics at Florida State University. And today she'll be talking to us about the Bayesian model for joint, longitudinal, and survival outcomes in the presence of subpopulation heterogeneity. So thank you very much for being here today.
Thank you very much. Good morning. So this is joint work with Peng Peng Wong, who is now my former student. She's just graduated. And Jonathan Bradley, a colleague of mine at Florida State University. And the idea is that many clinical studies these days collect this joint kind of data, some longitudinal outcome and a corresponding survival outcome. And I mean corresponding in the sense that we expect that there's some dependence between these two processes within an individual. And therefore, if we could jointly model them, we might do better in inference about the longitudinal outcome because we've utilized information from the survival outcome. And similarly, the reverse, that is, I could have better inference about survival outcome using information from the longitudinal outcome. This is not new. It's been around for a long time. And I'll give you a little overview after some motivation of approaches that have been taken to joint modeling. And then I'll delve into our variant with this particular work. So our first motivating example is this HIV data example, which is available in R. There was a clinical trial that looked at CD4 cell counts over time as the longitudinal outcome, and survival time as time to death or censoring as the survival time outcome among these individuals in a clinical trial. A second motivating example is the nutritional prevention of cancer trial, where in this case we have longitudinal prostate-specific antigen measurements. So we heard a little about PSA yesterday. And here I've transformed them by taking the log of PSA plus 1. And the reason to do that is it sort of pulls in some right skewness behavior in the PSA and allows us, the plus 1 allows us to take that log even though we may have PSA readings that are technically 0 in our men. And what I'm showing you here is if we consider on the left panel men who've not been diagnosed with prostate cancer, sort of what's the typical shape of a PSA trajectory over time. And in the right panel, a man who has been diagnosed with prostate cancer, what's the typical behavior of their trajectory of PSA, where time of diagnosis is just typically the end of the readings for these men in the right panel. And in the left panel, these men have not been diagnosed with prostate cancer. And so we've sort of put them on the clinical trial scale here as just time since randomization into the study. So do you think there's a difference in the shape of the PSA trajectories over time? I'm just showing you a low S curve here on this log scale. So if we could jointly model the PSA and the time to prostate cancer, say, or jointly model the CD4 cell count and the survival time of the participants in that study, we may do better at inference about each of those outcomes individually. So one approach would be to model one outcome conditional on the other and then have a marginal model for the outcome we conditioned on. So the survival outcome, say, conditional on the longitudinal outcome times a marginal model for the longitudinal marker, typically called a selection model or a measurement error model. And you see a lot of this joint modeling work evolved when there was a strong emphasis on AIDS research in biostatistics. So that was around the 1990s. A lot of work adopted that approach. Or you might reverse the conditioning, right, and have a marginal model for the survival outcome, often termed a pattern mixture model. Again, this was developed in the AIDS context. Well, at least it became more popular then. And a third approach I want to emphasize today is the idea of introducing latent variables to help us think about the dependence between these two outcomes that are quite different in nature, right? The longitudinal outcome maybe is measured as a continuous outcome at each time point, maybe it's an ordinal outcome, but it's nonetheless quite different from a time to event outcome that would have a censoring issue associated with it. In latent variables, let me just look at a little more detail here. I'll introduce now the notation that perhaps Y is our longitudinal marker, measured at distinct times for each individual. Let's let T be the event time of interest, the survival time outcome, say. We might adopt a shared random effects model where B is the shared random effect here, and you notice that what it's doing in this formulation is allowing that conditional on B, the two outcomes are independent, and the dependence between the outcomes is induced through that random effect. So that's what I mean by simplifying modeling the dependent structure. We just make this assumption that conditional on this latent quantity, the two outcomes are independent. If the latent variable is discrete, we now have a latent class model. So now we can think about partitioning our population into subgroups. And conditional on the subgroup, knowledge of the subgroup, the two outcomes are independent, but dependence between the two outcomes is induced by marginalizing over that subgroup. And this is particularly handy if we're thinking about accommodating heterogeneity within our population. So we have one population, but it's got some extra heterogeneity. And we may even have some variables to help explain that heterogeneity that we could introduce into the model for this latent subgroup. If the latent variable is, say, a whole stochastic process, we can still use this idea of conditional independence, conditional on the latent variable, to simplify the dependent structure. Today I'm going to talk about a model that really fits more in this latent process formulation, and it's building upon this work of Brown and Ibrahim in 2003, where the longitudinal outcome is modeled as having some trajectory shape over time plus a random error. And then a survival time is modeled in terms of its hazard function, where the hazard function is a function of this trajectory directly, right? So I can think about this longitudinal mean trajectory shape, say, as the latent process. Maybe it's just a linear form, maybe it's a quadratic form. You could do something much more fancy if you want to. Typically, the errors in this longitudinal process are assumed Gaussian with mean 0, so that this psi trajectory function is the mean of the longitudinal outcome. In particular, Brown and Ibrahim took these errors to be Gaussian. And this parameter gamma then is a key parameter because it's linking the longitudinal outcome and the survival time outcome in the model. I'll just point out here that the hazard function has some baseline hazard rate, lambda, which we in this talk will model using piecewise constant shape. And we can introduce additional covariates into the hazard function. For today, we're just going to look at time-independent covariates, so just baseline variables. And alpha is the coefficient associated with these variables in the hazard function. The model is completed by specifying prior distributions on the quantities, the unknown quantities in there. And to handle heterogeneity, we might suppose, say, a Dirichlet process prior on the regression parameters beta that appear in this trajectory function. Okay, so notice that these are subject-specific parameters. So each subject has his own trajectory function, quantified through a difference in these parameters, beta. And so the betas we might envision as arising from a Dirichlet process prior. And you may recall that in this kind of model, the inference about the distribution G, so the distribution G will be almost everywhere discrete. So that means subjects will tend to share values of these regression parameters beta in clusters. So this is a way to handle extra heterogeneity in the population. This is sometimes just thought of as a very flexible, essentially Bayesian non-parametric model for these regression parameters beta. But it does have this side effect of inducing a clustering in your population, and it's that side effect that I'm using here to accommodate extra heterogeneity in the population. So commonly in this kind of setup, and particularly Brown and Ibrahim did make this assumption, firstly of Gaussian errors on the longitudinal process, secondly, a Gaussian base distribution for this Dirichlet process prior distribution on the regression parameters. And thirdly, if we look at the rest of the model parameters, a Gaussian distribution was assigned for the parameter that links the survival and longitudinal process, and a Gaussian prior distribution for those regression parameters alpha in the survival time outcome. I just want to highlight those Gaussian distributions that sort of pervade this model setup. These lambdas are just the piecewise constants in that baseline hazard function for the survival outcome, so lambda L. Right? So why all these Gaussian distributions? Well, we think the Gaussian distribution is very nice, right? And we notice that approximate normality is very widespread in nature. We also notice that it's very easy for us to interpret. I can sort of summarize a Gaussian distribution by its mean and its standard deviation, and think about a mean plus or minus 2 standard deviation using an approximate interval estimate. Right? But what if there's something that's not nice about the Gaussian distribution in this model? Let's look a little closer. If we use all those Gaussian distributional assumptions, then the contribution to the joint likelihood, joint here meaning the longitudinal outcome and the survival outcome treated jointly as the data, the contribution from subject I has this form. And what you see is the first part, this is the longitudinal marker is assumed to have a Gaussian distribution. And the second part comes from the survival time outcome. And I want to highlight in red here this sort of double exponential form that's appearing in the survival time part of this model. And thinking about prior distributions for the parameters in this model, this likelihood sort of doesn't bring to mind a known distribution for you in terms of what would be a conjugate prior distribution for this likelihood function. It doesn't prevent us from fitting these models with this, right? It just means that when we go to calculate posterior distributions for that model setup that I've described, this is sort of a Gibbs sampling algorithm for doing it. And what I'm showing in gray is that there are a number of steps where within the Gibbs sampling iteration, we have to do some kind of iterative sampling. So the unique values of the regression parameters in the longitudinal trajectory, for example, have to be updated using Metropolis Hastings or maybe an adaptive rejection sampling kind of algorithm. So embedded within the Gibbs sampling loop is additional iterative steps are needed. Similarly, that key parameter that's linking the longitudinal and the survival process has to be updated in an iterative way within each Gibbs step. And also this regression parameter in the survival time part of the model. Okay, so computationally, certainly it's doable. We have the power to do this kind of thing, but it's maybe not as nice as we would like if we had had a nice conjugate structure for the model. What I mean by nice is that we think that the full conditional posteriors would be easy to sample from. So what can be done about it? Well, let me introduce you, or remind you perhaps, about the log gamma distribution. The log gamma distribution here is defined this way. If we have a random variable z that has a gamma distribution, and then we transform it by taking the log, we get a log gamma distributed random variable. It's a little counterintuitive if you do a lot of work with log normal distributions, because it's not quite the same definition. But let's think about the log gamma distribution for this model, and the reason is the PDF of a log gamma distribution has this kind of double exponential form that we saw in the likelihood in this joint model. So now I'm beginning to think about a distribution that can sort of mimic that distributional form in the likelihood function. The log gamma distribution can actually approximate a normal distribution. So if I think about replacing some of those Gaussian distributions with a log gamma distribution, I'm not really giving up much, because in the limit I can get a log gamma that approximates a Gaussian distribution. And actually I'm maybe buying something because I have a more flexible distribution. I can capture non-normal behavior, perhaps. To use the log gamma in the model setup that I've introduced to you, we're also going to need multivariate versions of the log gamma distribution. And Jonathan Bradley has a paper that I've cited here, and it's in the references at the end, where he works out a lot of the distributional theory for multivariate log gamma distribution of this particular form. I won't go into too much detail here. I just want to say that there is such a thing as a multivariate log gamma distribution that's formed in a fairly intuitive way, right? And it's parameterized here by these 4 parameters, and the one thing I'm noting is that this V matrix that's sort of governing the dependent structure in this multivariate log gamma here is a square matrix. And I want to contrast that with another kind of multivariate log gamma. Let me skip ahead. Oh, I won't skip ahead. Sticking with this multivariate log gamma distribution, if you work out its PDF, again you get this nice double exponential form. So we sort of see the form of the likelihood mimicked in this distributional form. And also, it can be shown that again, in the limit, we can get a multivariate normal distribution type behavior from this multivariate log gamma distribution. The other multivariate log gamma distribution I wanted to introduce you to is the conditional multivariate log gamma distribution, because we use this in our model formulation. And it's very intuitive. If you take a multivariate log gamma and you kind of think about the distribution of one part of it conditional on the other part of it, we derive a conditional multivariate log gamma distribution. And one difference is that this matrix H doesn't have to be square anymore. And so the PDF, this H is sort of playing the role of that V matrix that we saw in the unconditional multivariate log gamma distribution. But here it doesn't have to be square, and so that means we need some additional care when we think about sampling from this distribution. But again, the PDF has this nice double exponential form. That's the key for us today. Let's revisit the model formulation, but now instead of assuming that these errors on the longitudinal marker are Gaussian, let's suppose we give them a log gamma distribution. This is just the scalar log gamma distribution here. Now, our likelihood function has this sort of log gamma form coming from the longitudinal outcome part, and which has that double exponential form, right? And a similar double exponential form coming from the survival part of the model. So now there's a thought that by combining these and using this log gamma distribution, you might have a nicer, anyway, sort of conjugate structure. So what's needed to get that structure? We need some additional changes. We'll still keep the Dirichlet process prior on the subject-specific parameters in the longitudinal trajectory. And I like that because it's going to accommodate the heterogeneity in the population. But now we'll take the base distribution of this Dirichlet process to be a conditional multivariate log gamma distribution. We'll get that double exponential form coming in for us. Additionally, we'll change the prior distribution on the parameter that links the two outcome processes to a log gamma distribution. And we'll change that, what was previously a Gaussian distribution for the regression parameters in the survival part of the model, to a conditional multivariate log gamma distribution. And then what happens? Okay, now if we want to use a Gibbs sampling type algorithm to implement this model to get at the posterior distributions, there's just one step where we have to do some iteration within the Gibbs iterates. And that's this alpha epsilon, kind of buried in here. It's the one of the parameters for the log gamma distribution for the errors. By the way, we introduce a constraint here so that the mean of the errors is 0, so that this remains sort of an unbiased trajectory function for the longitudinal outcome. So the sort of idea was to take what was an interesting model for joint survival and longitudinal outcomes that accommodates heterogeneity in the population through this Dirichlet process prior on the regression parameters in the longitudinal outcome part of the model, and hopefully get some computational gains by reformulating that model using a log gamma distribution instead of a Gaussian distribution. And there are sort of less iterative steps needed in the Gibbs sampler. But we did find that sort of care is needed in sampling from these log gamma distributions, particularly the conditional multivariate log gamma distribution. And in this step, we explored different ways to do this sort of iteration, and we ended up settling on the slice sampling step as a good way to do it in our algorithm. I'm only going to show you results for the slice sampler in here. So let's look now at a simulation study. And the simulation study generates the data conforming to our model in either the Gaussian framework or the log gamma framework. So we generate data that's truly Gaussian or truly log gamma. And then we fit the model with either the Gaussian formulation or the log gamma formulation. And additionally, we'll generate data having 1, 2, or 3 clusters. So there will be this underlying heterogeneity in the population with respect to the longitudinal outcome. And that induces, of course, a clustering structure in the survival time outcome, because remember the longitudinal trajectory function is a predictor in the hazard for the survival outcome. Here's an example of a simulated data set. If we look at the left 2 panels, I'm showing the longitudinal outcome. Nice. By the way, we're fitting the linear longitudinal outcome model here, so just an intercept and a slope that's specific to each individual in the model. And whenever an individual has this event, we no longer observe the longitudinal outcome, so it kind of thins out as individuals are dropping out because they're experiencing their event. At the bottom left is the corresponding hazard rate for each individual. Right? And it's piecewise linear. The baseline hazard rate is piecewise linear, but this is actually piecewise constant. The baseline hazard is piecewise constant. The hazard for an individual will be piecewise linear because we have this longitudinal marker as a predictor in this hazard function. So we simulate data with 1 cluster or with 2 clusters in the middle 2 panels, and with 3 clusters in the far right panel. And we want to evaluate how well our models perform if they assume the Gaussian structure that this data has, or if they assume the log gamma structure. We also simulate data assuming the underlying log gamma structure, and it looks very similar. Right? In fact, the log gamma distributions that we're using here have a small amount of skewness, not a huge amount of skewness. They really aren't that far from the Gaussian distribution. So our model is this again. The errors on the longitudinal outcome are assumed to be either Gaussian or log gamma, and the corresponding other changes to the model that are needed. We ran the Gibbs Sampler, 2,000 burn-in iterations, 3,000. 2,000 seems sufficient for the burn-in for the parameters in the model. We have 3,000 inferential iterations, and we're going to look at the fit of the models both at the individual level and at the cluster level. So at the cluster level, we actually pick the best iterate among the inferential iterates using Dahl's method for doing that. Right? So there's a way to sort of say what's the best one, and then we use that in terms of making inference about the cluster structure. Okay, here I'm fitting the Gaussian model to Gaussian data, and I'm showing you just the results where there are in fact 3 clusters in the simulated data. And those 3 clusters have linear trajectory functions for the longitudinal outcome, the intercept, and slope. There's only 6 because all the subjects in the cluster share the same values of those parameters. And I'm showing in the second column the bias of our parameter estimates, and then a credible region in the last 2 columns. And a problem here, I've highlighted in yellow, is that we seem to have relatively a large amount of bias in this key parameter gamma that's linking the 2 processes. Gamma here is -1. So as the longitudinal marker increases, right, there will be a reduced hazard for the event of interest. So our estimate appears to be a bit biased, but the model is detecting that gamma is significantly different from 0, right, and is significantly less than 0. These lambda parameters, I'll remind you, are just the constants in the baseline hazard rate function. That's assumed piecewise constant. There's a little bias in the estimate of these parameters also. At the individual level, this is just showing 6 individuals, 2 from each cluster, their longitudinal trajectory. The line is the estimated longitudinal trajectory, and the circles are the actual data points that we have available for those individuals. So by eye, you might think that looks okay. Same thing for the hazard rate functions. We can just look at the individual level, how well do we seem to recover the underlying hazard functions. But now let me change, let's take that same Gaussian data, but now fit the log gamma model. Here, that bias in this key parameter linking the 2 processes is significantly less. We're still estimating it pretty well. In particular, we're saying it's significantly less than 0. We seem to be doing better than if we actually use the Gaussian model on the Gaussian data. We seem to be doing better just by switching to the log gamma model, even though it's not the model that was used to generate the data. That's the observation I'm going to make here. At the individual level, we can summarize sort of that behavior that we saw in the plots for the individual by looking at, say, mean square error in the estimation of the longitudinal trajectory and the hazard rate function. So this is just looking at the sum of squared errors for estimated values around the truth. And I want to highlight the bold numbers here. So in the longitudinal outcome, the bold numbers are always corresponding to when the Gaussian joint model is fit. regardless of how the data were generated. So what that's saying is the bold numbers are slightly less than the non-bolded numbers. So the Gaussian model fit seems to show less mean square error in the longitudinal outcome, no matter how the data were generated. If we look at the estimation on the hazard rate function, when the data are Gaussian, the log gamma is showing a little less mean square error in the estimation of the hazard function. When the data are log gamma, the Gaussian model, well, sorry, take that back. In this one case, the Gaussian model is showing less mean square error in the hazard rate function. In the other two, it's still the log gamma model. Quick summary here would be the Gaussian model seems to better fit the individual trajectories, regardless of how the data were generated. The log gamma model seems to better fit the hazard rate functions. What about at the cluster level? Again, if the data are generated either Gaussian or log gamma, we fit either the Gaussian or the log gamma model. And then we can think about estimating the number of clusters in the data. And this is based on that best iterate that we get from our inferential iterates from the Gibbs Sampler. And by the way, that's sort of averaged over the replicates of the simulation that we're doing. So here, if the true number of clusters is 1, we get an estimate that's a little closer to 1 if we fit the log gamma model, even if the data were Gaussian. Right? If the true number of clusters is 2, again, we're a little closer fitting the log gamma model, even if the data were Gaussian. We're a little closer fitting the log gamma model, even if the data were Gaussian. And you see from the bold numbers, that's sort of the pattern here. And it's interesting because the Dirichlet process prior that we're using here is known to overestimate the number of clusters. I mean, it's not consistent in terms of estimating the number of clusters. So I expect some overestimation. But it's interesting that just by changing the model formulation, we seem to have less overestimation with the log gamma structure than we had with the Gaussian structure. The last column is the adjusted RAND index. We were also introduced to that earlier in this meeting. And the adjusted RAND index, the higher the number, the closer to 1, the better. Right? So how well are we recovering the assignment of the subjects to the clusters? And we're doing a little better if we fit the log gamma distribution, except in this one case, there's only one cluster there. So I'm not quite ready to summarize the simulation results yet. Let me just show you a little more about it. So suppose we have Gaussian data. We fit the Gaussian joint model. This is what we find in terms of inference for the longitudinal outcome and for the hazard rate function at the cluster level. So what you see is 3 red lines. There are actually 3 clusters in the data. The red is the truth. And you see a lot more blue lines. So the Gaussian model with Gaussian data is finding too many clusters, typically. Right? Well, we kind of expect that from the Dirichlet process. On the other hand, when we fit the log gamma model, we actually recover the right number of clusters. That's what I was just showing you here. There's sort of less overestimation of the number of clusters with the log gamma formulation than there is with the Gaussian formulation. Here, if we simulate log gamma data and fit the 2 models, again, we see that the Gaussian model is overestimating the number of clusters by more than the log gamma model is. So, let me highlight one more thing, which is one of our motivations for this reformulation of this joint model from the Gaussian structure to the log gamma was to gain in computational efficiency. Right? We thought, well, we'll get more of a conjugate-looking structure. That should help us in our computation. And what I'll show you here is the effective sample size of the 3,000 inferential iterates of the Gibbs Sampler under the two model structures with the two kinds of simulated data. If I generate Gaussian data, I fit the Gaussian model, I do 3,000 iterates, I have an effective sample size in the 2,000. If I fit the log gamma model, the effective sample size is actually 3,000. This is the effective sample size that kind of corrects for the correlation in the iterates that you're getting over the 3,000 in the inferential part of the chain. If we have log gamma data, we fit the Gaussian model. Again, we pay a price in terms of the effective sample size of our chain. So to summarize, at the individual level, making inference about the longitudinal outcome appears to be better from the Gaussian model, right? The mean square error was smaller. Inference about the hazard function is actually a little better with the log gamma model in terms of mean square error. Inference about the clustering itself, the cluster assignments, and number of clusters. The number of clusters we appear to do better with the log gamma model regardless of the nature of the data. And the adjusted RAND index is a little better, again, under the log gamma model formulation. Inference at the cluster level, so the cluster level parameters, is better for the hazard function using the log gamma model and sort of roughly the same under the two model formulations for the longitudinal outcome. Sort of high-level summary I wanted to share. And let's gain a little more insight by going back to those two motivating examples and see how these two model formulations perform. So let's look at this HIV data. Again, we've got longitudinal CD4 cell counts over time and time to death as the survival time outcome. There are actually two underlying treatment groups here, and we incorporate the treatment group information and some other covariates in the covariates in the survival time part of the model. If we fit the Gaussian joint model in the top panels or the log gamma formulation of the joint model in the bottom panels, here's an idea of what the fits might look like on the CD4 cell counts, here transformed by taking the square root, for some individuals in the data. Right? So by eye, it's hard to say that one formulation is better than the other. However, if you combine across all subjects, you find that fitting the Gaussian joint model, the mean square error here is about 0.08, and the log gamma model mean square error is about double that. That's consistent with what we saw in the simulation results. The Gaussian model is fitting the individual outcomes better. Why is that? Recall, the Gaussian joint model in our simulation study tended to overestimate the number of clusters by a lot more. And that's what we see in these real data analyses. The Gaussian joint model was finding 38 clusters, whereas the log gamma joint model was finding only 7 clusters in the data. Now you can begin to see, oh, if we're finding so many more clusters, of course we're going to do better at predicting the individual outcome data, right? The mean square error will be less. Clinically, though, does it make sense when you go back and talk to clinicians about 38 clusters in these data? It's much harder to try to interpret. What we're showing here is the cluster level CD4 cell count trajectories, the cluster level hazard rate function estimates, and then the cluster level survival functions. And in the middle of this survival function is just a Kaplan-Meier curve that you would get if you just fit the survival time data only. But we also did a little analysis to see, do we do better by using these two outcomes jointly than if we just look at each one separately? And in this example and also the PSA example, we do learn something, we do gain something by combining the information over the two outcomes. For these HIV data, We fit again just that linear trajectory function, and we see that if we fit the Gaussian formulation of the model, the slope in the linear trajectory function is not technically statistically significant, whereas with the log gamma model, it's maybe statistically significant there. But a key parameter is this gamma that links the two outcomes, and we do find that it's statistically significantly negative, regardless of our model formulation. Right, so as the CD4 level were to increase, there would be a less chance for death occurring in these data. Some of the other covariates in the survival time outcome were also statistically significant. The treatment group assignment, gender, use of ACT were statistically significant, but this previous opportunistic infections is actually not statistically significant in this model. Let's move on to the PSA data example. Here is a look again at some of the possible shapes in the PSA trajectories. Here it is on the log transform scale. And we're going to do our analysis on this log transform scale. Let's look first at the parameter estimates. So I want to highlight this parameter gamma linking the two processes again. Here it's positive, right, regardless of which model formulation we fit. And again, a positive value would show that larger values for the PSA would make one more likely to have the event of interest here, which is diagnosis of prostate cancer. So that makes sense also. As far as performance goes, again, we can look at some individuals, how well do we recover their longitudinal trajectory in the two model formulations, and summarize it over individuals using this mean square error. And by now, well, that's interesting. So the Gaussian joint model here, I'm reporting a mean square error of 1.7, and in the log gamma, a mean square error of 4.94. Not quite sure if that's correct, because our intuition is that the Gaussian model will tend to fit more clusters than the log gamma model. In fact, the Gaussian model found 56 clusters in these data, and the log gamma model found 7 clusters. So again, would you want to discuss 56 individual clusters with the clinicians involved in this study? So I didn't emphasize this point too much, but we did investigate that we do learn something. In fact, we have proved precision about inference of the survival outcome by incorporating the information from the longitudinal outcome and vice versa in these data. And that's to be expected because we are finding this statistically significant association between these two outcomes through this parameter gamma. I like this idea of using the Dirichlet process prior to enable this discovery of subgroup structure in the data. It does have the known property that it tends to overestimate the number of clusters. It tends to yield a number of very small clusters that very often people will sort of, in a post hoc way, merge those very small clusters with other clusters that were discovered using the Dirichlet process prior. We've assumed a common population parameter gamma linking the two processes. You could consider maybe a cluster-specific parameter there, allowing the association to go different directions in the different clusters. The log gamma formulation, we argue, increases flexibility because we're allowing for some potential skewness in the outcomes in the model, and does provide a conjugate structure by replicating that sort of joint double exponential structure that appears in the likelihood for this model. Sampling still requires some care, but one thing is we did find the computation was more efficient with respect to the expected sample size, effective sample size in our sampler. So thank you very much. Here's some key references. In particular, this Bradley paper is the one that talks about the distribution theory for the log gamma distributions that I introduced in this talk. Thank you. Okay.
Do you have a sense for whether the clusters that are being found are interpretable in some sense? Like, you have sort of feel, certainly the 7 might have a hope, and the 52 probably not.
Exactly.
56.
56. Yeah. So the 7 here. I can speak from another experience with these data also that I just can't help but bring to bear here. That is, an early analysis I did of these data was the latent class analysis. So I assumed that conditional on knowing what class an individual belonged to, the longitudinal outcome and the survival outcome were independent. And in that analysis, we found 3 or 4 distinct classes in the data. And we argued they were interpretable. I just want to drive 2 things home. One is, yes, sometimes you can make up a really nice story around the classes that you find. For example, it's not unusual that there'll be some individuals that have a very low PSA. So typically if a man is healthy, we expect his PSA to grow very slowly over time as he ages. And once cancer initiates, then the PSA will tend to grow exponentially. So we kind of expect that there's a group, since in our data we have both men who've been diagnosed with prostate cancer and men who've not been diagnosed with prostate cancer. Yesterday we heard about Chris Morrell's data set where everyone had been diagnosed with prostate cancer, but here we've got both. So we expect that there would be some where we expect a cluster to represent the healthy men and another cluster to represent men who've been diagnosed. But we also know there's some messiness in the data because among the men who've not been diagnosed, cancer could still have initiated and hadn't been detected yet. These particular data were collected in the 80s and 90s before the era of widespread PSA screening, which makes it these data extremely valuable. It's hard to get such long series of high values anymore. So I'm not sure about 7, but I could interpret a few of these very well. What's interesting is in this model formulation, I don't see a behavior associated, say, in this top curve, the very high PSA level. This is the men who are going to be diagnosed with prostate cancer very quickly. This green line here, right? Their survival curve drops off very quickly, which means they're removed from the data. We do not have PSA reading after they were diagnosed with prostate cancer. In some of the earlier work, I'd actually seen this very high trajectory of PSA starting to come back down because the men with the highest PSA were being removed from the data. Interestingly, I'm not seeing that here, and I'm not quite sure why this model is not having that behavior. But the caution I want to make about this is the cluster structure is another way to capture some of the dependence between these 2 outcomes. So if there is dependence, not so much in this model, but a little, and more so in the latent class model, cluster structure will be found just to accommodate the dependence. So I caution against over-interpreting the cluster structure that's found. So it would be important to sort of tease out how much of it is needed to capture the dependence and how much of it is truly present in the data. Here, this model has this parameter gamma also capturing the dependence. And so that leads me to sort of have more trust in the cluster structure that emerges from this figure. Thanks for the question. David, you have a question?
Your summary captured both of the questions that I wanted to raise, but let me go back and just sort of underline things. I really like the idea of using the Dirichlet process clustering to capture the heterogeneity, but the set of construction makes it really clear that it's going to be, the number of clusters is going to be determined by your model, not by the data. And so obviously you're going to need to find some way to come back and reaggregate clusters or otherwise sort that problem out. And secondly, the gamma parameter strikes me as a very low information channel for capturing the types of dependency that might be going on. And so I wonder if there are ways to make it multivariate or otherwise extend it. You were talking about making it separate for different gamma for each of the clusters.
Yes, I did mention that.
But that's still...
That doesn't satisfy you. That's still low information?
Yeah.
Let me just see if I can
Just one
have us all look at sort of this particular model here. The more you think about this, the more flexible it becomes. That's my experience with this. And part of the reason is these subject-specific trajectory functions, right? So it is constraining that the value of this trajectory function being high or being low within a subject, sort of, if it's increasing in time or decreasing in time, the sign of gamma is going to sort of be fixed, right? Because it's the same gamma for everyone. But some subjects can have an increasing trajectory function. Some subjects can have a decreasing trajectory function. And so how you interpret it, it's sort of like, are you going to fix a point in time and think about it, or are you going to look at a change in time within a subject or look at two different subjects? I agree it's not capturing perhaps every aspect of dependence between these processes. But I think it's a useful way to think about it.
In your application, the fact that it was statistically significantly different from zero says that you are certainly drawing information out of there that's valid and real. It just, it seems a little reflexive.
I do take home the message that you just made in the applications. The fact that gamma is statistically different from zero is informative to us. It's telling us there is something to be learned by looking at these two outcomes jointly. And maybe there's more to be learned if we could make that part of the model a little more flexible. I won't disagree with that. Thank you, David.
In all two situations you outlined, gamma had a magnitude close to 1. Is there any reason to expect that, or is it just coincidence?
I think it's coincidence. The reason our simulation was designed that way was because we were seeing that kind of behavior in the data.
Mm-hmm.
Why it's in the data that way, I think has some impact on perhaps how you scale things. Thanks.
All right, let's thank her again.